So the shortest path, we adopt the directed graph, or sometimes we call it digraph. In the digraph, okay, there are some concepts that we can learn, and yeah, we are going to learn the concept of transitive closure. And there will be one algorithm that we will learn in this section, which is Floyd markup. Directed graph. We know that the word directed, it means there is a direction. There is a direction from one node to another. This is an example of the airport. So we have a node which is the airport LAX, Los Angeles, and there is a flight from LAX to Oregon. So the diagram is a graph whose edges are all directed. Okay, we have the direction, we have the direction, we have the direction. It is the short for the directed graph. And the applications will be, for example, if you want to find the shortest path. So the shortest path means if the shortest path should apply the directed graph, then it may be one-way street. Or if it is applied, there will be only one way. You can have another way if it is a round trip or task schedule. So the property of the diagram, it is the same with the graph, except that the x, so a graph G, it has V, which is vertices, and then we have E, we have the edges. Each of the edges goes in one direction. So this edge is going to one direction. This edge is going to one direction. Edge A comma B goes from A to B, but not B to B. So if this one, I have the edge A to B, then it means I can say there is a way from A to B, but this is not a way from B to B. Okay, so if G is simple, simple means you have only one edge from one node to another. So here is one of the simple. We have the properties like this one. M is the number of edges. N is the number of vertices. Then the property will be M is less than equal to N multiplied by N minus 1. Yeah. Then this is the graph. If we keep in edges, you remember what? So in D, we have 1, 2, 3. There are 3 in edges. In A, we have 1, 2, 3 out edges. So sometimes we call it incoming edges, for in edges, okay, or sometimes we call it in edges. It is also possible, or sometimes we just call in edges like this one. Outgoing edges. Sometimes we call it as out edges. Sometimes we call out edges like this one. So those words are the same. If we keep in edges and out edges in a separate adjacency list, so we can perform listing of incoming edges and outgoing edges in time proportional to their. So if we put this one in one adjacency list and we put this one in another adjacency, then the listing of this one, the performance time will be proportional to that. It means the number of edges, so it will be O, it will be OM. It's proportional to the time. There are some applications, for example, in the scheduling. The scheduling means you need to follow the flow. I can do ICS 22 after I finish ICS 21. I can do ICS 23 after I finish ICS 23. So the X A, B means a task must be completed before B started. Task A must be completed before task B can be done. Then we can have a diagram or diagram. In DFS, if you still remember, okay, that first search, okay, DFS, depth first search, and then we have DFS, okay, we have the breadth first search. And this chapter, we learn the graph is undirected. The graph is undirected. What does it mean? There is no direction. There is no particular direction from one node to another node. So it can be A to B, B to B. We can specialize the traversal algorithms, which is DFS and BFS, to diagram. So you can make a special traversing algorithm for the directed graph by traversing edges only along the curve. So if there is no direction, yeah, you can say I can go from C to E, E to C. But if there is a direction, you can only go along with that. So in the directed DFS algorithm, there will be 4 types of. Do you still remember in the DFS? How many categories of the edges at a time? We can have discovery edges, and then we can have the back edges. For the BFS, what are the category of edges? We have discovery edges and we have cross edges. Okay, so please look at the material before. In this case, there will be 4 types of edges. The first is discovery edges. It means we discover, or this is the first time to visit the edge. We have the back edge. So this adds return back to another node we can visit. we can have forward edges. Forward edges means an edge that will be in the next step. And there will be cross edges. The cross edges means this is the same with the PM. The node in the same level. So directed DRS starting at a vertex S, that means the vertex reachable from S. Okay, the keyword is reachable. So we need to find what is the possible path so it can be read from S, which is A, to E. Or for example, I want to go from B to E. Then it means I need to find the way from B to E, or we need to find all the vertices which is reachable from. So the idea is we need to find the reachability. When we have the reachability, we will create a tree. So do you remember the data structure tree? In the tree data structure, we need to have root. So we need to have root. So the root will have child. And then we can have child. We can have child. So if we have this kind of tree, this is the binary tree. Okay, if you still remember, this is the binary tree because each of the node have two childs. Okay. So this is the root. If you still remember, the root is the top node. So for this is reachable from V via directed path. So we need to find if V is the starting point, then there should be a tree. So there should be a tree, something like this one, starting from this root, going to another node. So for example, if I want to start from C, so using this graph, now I want to start from C. I want to start from C, then there will be a tree. The tree is this one, C from C to E, and then from E to A, from E to D. So this is one point. For example, I want to start from B. Then there will be a tree. This is from B to F. This is from B to D. This is from B to A. And then we can see this one. If you want to go from B to E, yeah, there will be only one way, which is you need to go to C, and then from C you can go to E. So this is the ring ability. Question is it possible to find the reachability from C to F? From C, we can go to E. E can go to A can go to C. So there is no reachable path to F. there is no reachable path to it. Okay, so that's why this is the reachable tree from strong perpendicularity means all vertex can reach all other vertices. So because of the time, maybe I will stop here. Let the break.